Okay, this is lecture 6 of our DTCO course. And first of all, sorry for missing lecture 6 in last Wednesday due to my personal matter. As I announced, I will make another recorded video for this missing one lecture. And let's just continue our original lecture content, lecture 6. Okay, so first of all, let's just start our today's lecture with a short discussion about the current status about FinFET. When we talk about high volume manufacturing, so here high volume manufacturing, it means that you sell it, you sell it to your customer. For example, if we consider very well known research institute called as IMAP, they can fabricate FinFETs quite well. So it is well known. However, we don't call it as a high volume manufacturing. So of course they can make certain chips, but it is not suitable for high volume manufacturing. So if we consider this kind of real fabrication, so commercialization of a certain technology, so as of today, so it is known that only a few companies can do such kind of high volume manufacturing, and they are listed here. And you can see that here one a little bit shaded line. So because this company is the last one to survive. So okay, so let me just explain a little bit more about this one. Here you can see that TSMC, so a company in Taiwan, and they have been the leader in the foundry industry for a long time. Actually, this TSMC is the very first company to start foundry industry. And their last FinFET technology was N3, and now they moved to N2 technology, and N2 is no longer using FinFET. But today's lecture will be devoted to FinFET, so we do not consider nanosheet MOSFET, which is even more advanced than FinFET technology. So anyway, they really enjoyed they did really well during this FinFET era and successfully moved to N2 era, N2 node, and now we say that now we are entering into nanosheet era. And there is another company, foundry company called as Intel. Maybe you have heard about this company so many times, and when you recall our presentation material for a quarter micron technology or 180 nanometer technology, actually Intel was the industry, the leading company in this industry for several decades, but due to certain mistakes in their technological decision, so they are now behind the TSMC, and their last FinFET was also Intel 3. Intel 3 is corresponding to so-called 3 nanometer technology, and yes, it is also their last FinFET node, and we are expecting their new nanosheet node called as 18A, but unfortunately this 18A was cancelled during their ramping up, and we are now expecting their 14A technology. Here A is corresponding to a unit angstrom, maybe you know it, so this one angstrom is corresponding to 0.1 nanometer, and they changed their naming convention to this kind of thing, because you know 1.4 nanometer or 1.0 nanometer seems to be too, how can I say, too unrealistic, so they just introduce this kind of a naming convention. But I think that it is just naming, brand name for them. Anyway, anyway, the future of Intel is not that certain. So I cannot, at least I cannot predict what will happen in near future about Intel, because although they are struggling to fabricate their newest technology, but it is also certain that since Intel is the only remaining US company remaining in this scene, so semiconductor in chip manufacturing, so they are getting a lot of support from government level. So maybe you have heard about, so US government owned the stocks, Intel stocks, quite a lot in these days. So what will happen to Intel, especially its foundry service? I have no idea about the future. And we have another company called as Samsung, and since we are South Korean, many of us, so we know Samsung quite well. And this company is ranked as number 2 in the foundry industry, but far beyond this first one. The first one is having the market share higher than 60%, and it's Samsung's share is about 10 something percent, and they are quite close to the third one. The situation was not that bad a few years ago, but they made continuous failure to follow the TSMC's progress. So they announced some nodes, say that we are the first one to develop number 3 nanometer node. Yes, they announced first, but actually failed to secure big customers. So several failure cases were reported. But anyway, still, it is true that there is only a few options for us to select the state of the art foundry companies. Samsung is the second one, and their last FinFET is a little bit different because they call it as 4 nanometer technology, and their first nanosheet technology is called as 3 nanometer. So they moved first. We wanted to move to the nanosheet era a little bit earlier than TSMC, but changing architecture from one to the other. For example, from planar MOSFET to FinFET, or from FinFET to nanosheet MOSFET takes a lot of effort, and we have many errors, and so that's the reason why they are still struggling in their 3 nanometer technology and other ones. So their newer one, like a 2 nanometer, yes, 2 nanometer was actually announced in few months ago in VLSI technology, but so it's not certain what will happen to its future node, so that is still questionable. So let me just summarize the discussion up to now. There are 3 companies well known to Western, kind of West, well anyway, certain world, and they are all finishing their FinFET node. So their last FinFET node, and all of 3 of them are now moving into nanosheet era. So if we just consider this situation, maybe you may think that, oh, FinFETs are widespread and quite common. It is easy to find. However, situation is completely the opposite. So let me just go to the first one. The first one is SMIC. This is a Chinese company, and it is, because I have used the term like reportedly, because it is not certain, so they do not announce something about their technology. And this means that when they make, when they fabricate Huawei's most advanced AP application processor or other chips, then we can take it and make a certain investigation and says that they are fabricating chips almost equal to 7 nano technology. So this leaked information is used to make this statement. Well, anyway, SMIC is reported that they can make 7 nanometer technology without extreme ultraviolet technology, lithography, without EUV. So it is also reported that their technology is quite close to that of TSMC. TSMC also fabricated their 7 nano technology without EUV. After that, they introduced the EUV era. So, well, they are quite close, but people think that further scaling down to 5 nanometer and 3 nanometer will require the use of EUV. Without EUV, it would be very difficult to make it. Of course, they can make a few surviving samples, but it doesn't mean that they can do high volume manufacturing. High volume manufacturing really need very important criterion called as yield. So number of good chips over number of entire fabricated chips. So if this is around 60, 70, 80, it is regarded as a wonderful number. And when we have, for example, 10 or 20% for this yield, that is a really quite a low number and regarded as a bad sign for this logic technology. In the case of memory industry, numbers are a little bit different. So they really need even higher yield, over 80, 90. These numbers are required for their yield. But anyway, so SMIC can fabricate a 7 nanometer without EUV. That's the reason why Huawei can fabricate their cell phone quite, or their application processor quite competitive, at least within mainland China. So that is the one. And okay, so we have covered up to here. Then we can say that, oh, already we have found 4 companies who can generate 7 nanometer or 4 nanometer, 3 nanometer. Oh, FinFETs are easy to find. However, except for these 4 companies, there is no other company, known company, which can generate or fabricate FinFETs. For example, here we have the last victim of this competition. So this is a Global Foundry. Global Foundry was spin-off from AMD's, you know AMD. AMD is a fab, and they were first acquired by some Arabic capital. After that, they just left, and this Global Foundry stopped at their very first 12 nanometer FinFET technology. So they just enter into this FinFET era. However, when they come, actually they were a little bit behind the other competitors, like these competitors. So that's the reason why they could not get customers for their 12 nanometer FinFET technology. So I remember that whenever several years ago, whenever I visit IDM, International Conference for Semiconductor Devices, and they announced actively their new technology. But you know, this is not only the matter of engineering and technology, it is related with customer and capital. So although they were backed by really rich Arabic capital, but eventually they just stopped their development because orders of money required for this activity is really high. So that's the reason. So no further scaling. So effectively we can ignore this company, for FinFET technology. The reason why I'm showing this situation again and again is, let me just think about my last business trip to Munich, Germany. So I skipped one week for offline lecture for attending a conference. So European conference. So many experts in Europe came to there to discuss about future of European semiconductor industry. And surprisingly enough, although there are so many countries in European continent, 일부러 끈 거예요. 네. Although we have so many countries in European continent, and it is true that there is no company who can fabricate, unfortunately, this FinFET. There is no company at all. The only way they can fabricate FinFET is quite recently they have made a company called as ESMC. What is the E? This E is European. So European Semiconductor Manufacturing Company, and it is made by this TSMC. They just implement and funded by this TSMC technique. So the reason why I'm emphasizing this story again and again is this semiconductor chip manufacturing is only open to very limited number of countries and companies, and the competing itself is quite severe. So that is the main motivation of this kind of lecture. Why we have to do DTCO? Why we need optimization, even just optimizing technology, but why we have to do co-optimization even to improve the performance? It is only because now there are only a few competitors, and the advantages getting obtained from this winning competition is so huge. So think about this one. What is the gain of this competition? The advantages of Taiwan. Without TSMC, what happened to Taiwan? So please note that this is not just a matter of a simple engineering problem, and this is a really important one to us and to any others in the world if they are participating in this game or this competition. Okay, so that was just the situation as of 2025, and we currently in this classroom don't have a facility to fabricate it. So of course we have in the ground floor, not in this building, but the C1 building, we have a small fab. However, can you fabricate FinFET within that small fab? No, Actually, as you can see here, there are only 4 companies who can actually fabricate a FinFET. And the main topic of our lecture in this entire semester is not actually FinFET. We will talk about even nanosheet MOSFET, and then who can generate nanosheet MOSFET. If we consider nanosheet MOSFET, and the numbers are still getting reduced, so only these first 3 companies can fabricate nanosheet MOSFET in these days. So unfortunately, although we are quite much interested with semiconductor devices, but we have no capability to actually fabricate it, and the situation is quite common for many universities. So we will today use a different way to talk about our most advanced semiconductor devices. So in this semester, we will actively use a process emulator, which can emulate the fabrication process semiconductor of semiconductor devices, and this code specially developed for not only for this course, and still it is under development. So please understand the situation. Every week I will release a new version, and so you will find that grammar is changing every week, so please don't complain about it. So I'm doing my best to improve its capability. So anyway, in our lecture, if I'm not mistaken, so maybe L3, in our L3 you entered into our exercise workstation and just type Armstrong Craft, and it complains that you have to provide infinite name. That was the situation, and now you have an input file. This is the very first input file you will try in this course. Well, this is just a text file, and here you have certain lines. Actually, I think that this is the first line and second line and third line, and please do not try to understand the reason why it is written this way. The grammar itself is made by myself. I'm just to introduce so-called domain specific language. So simply speaking, I made it for this course, and that's the reason why you cannot find a similar one in other places. Okay, so let's go to the next one to explain it a little bit more. Here I have introduced a concept of a spec and body. It is not universally accepted one, just for a while. You only during in this class, in this semester, please accept this concept. Every statement in this command file, input file, have this form. There is only one single grammar. It is pre-reserved statement. You cannot generate a statement like, oh, I wanted to make a home statement. No, it's not possible. So you must know what is the reserved statement name, and in this case, craft is a reserved state name. The purpose of this craft means that generate a certain structure considered in this Armstrong Craft program. And now you have 2 different input arguments like spec and body. Why I separated these 2? So this code is written as a C++ language, and in this C++ language I have to initiate a class dedicated for this Armstrong Craft. when I generate it, I need some mandatory parameters to generate something. For example, let me just explain it. If I wanted to make this Ångström-Crafts world, then the thing I wanted to know before starting our journey is how large is our world is. That information is required before starting the creation of this Ångström-Crafts procedure. Okay, so that's the reason why when you have a look at this one, here we have Lx, Ly, and Lz. These three numbers are just specifying the length along x direction, and number along y direction, and number along z direction. It means that if we say that this number 1 is corresponding to 1 nanometer, if we assume this way, well, actually my original plan was this number is corresponding to 0.1 nanometer, 1 Ångström. That was my original intention, and that's the reason why I named it as Ångström-Crafts instead of nanometer Crafts. But currently, my implementation is not that efficient to support this really Ångström-wise resolution. So please, for a while, just regard this number, integer number, in nanometer unit. So simply speaking, it means that we have 162 nanometer, and y direction, that is 288 nanometer, and its height is about 400 nanometer. That is the world we can imagine in this one, and it means that please do not change it during our calculation or our process emulation. This is the limit of our world. Yes, this is the one. I will explain a little bit more about this selection of Lx and Ly later at the end of this lecture today. So also let's just think about this one. So region equal to deep substrate, and here we have a quotation mark, and the strings between these two quotation marks are regarded as a string. So you can say whatever you want, and thickness is 1. It means that when we start the initiation of this world, at least we must have the very first reason for starting this evaluation. So simply speaking, it means that now we have just a thickness 1 very thin structure, thin layer located at the bottom of this entire structure, and it is aligned in XY plane. We always assume that this z-axis is wafer perpendicular, one wafer normal direction, and x and y plane is regarded in our layout plane. Okay, when we have a look at layout, that is corresponding to x and y plane, and this z direction is just projected in our layout plot. So now you can understand, by specifying in this way, we will have a very thin layer whose thickness is just 1 nanometer, and its name is deep substrate. So you can always change its name. Instead of a deep substrate, just to say deep, it's okay. It's your choice. But point is, if you reuse this deep later, then they are recognized as the same one. You can use the same name again and again, then that will just add more and more for your already existing region. And here at the end of our spec, so there is a name for our output CGNS file. So I love Pokemon Monster, so that's the reason why I named it as this way. Okay. So now you can understand at the beginning of this initiation, we can have a certain box whose size is given, and it has very initial substrate, and now the result of its emulation will be saved as this name. That was the initiation part. After that, this body is the actual events we will have during process emulation. So now you can see that here body contains only one single statement, and this is depot. Depot is obtained from deposition, and deposit a certain reason substrate. Please note that this is a different name, deep substrate and substrate, so they are regarded as different regions. And thickness is just number 9, so it is also quite shallow, but this is just for our demonstration. So what you can expect is after this command file is over, then we will have the very first deep substrate, and we will have another one called as substrate, which is thicker than previous one. Its thickness is number 9, and we will have just 10 nanometer thick and wide structure as a result of this one. Please note that this depot, that is also once again statement, and it has here, it has spec, and it has although this depot is a body of craft, however it can once again have a body and spec again and again. It can be nested in this way. But you know, grammar is not completely universal. So if it doesn't work, maybe that is an error or your mistakes. So please do not try fix the bug. Then please just report me. Then I will try to fix a bug of this craft Ångström craft code. Okay, so I think that was already covered. This slide was already covered in my previous slide. Okay, craft object was created, and in order to creation, we need some information, and that was covered by our spec. And after that, we need certain body, and this body just to specify deposition of a single layer. Now we can expect 2 reasons in our structure, and let's go to the result of our exercise. So now you will find that there is a certain CGNS file. Its name is specified by your command file. If you change the name of this command file, name of your CGNS specification, for example, if I say a.cgns, then of course your final result will be saved, not this file, but a.cgns. You can do it, and it works as expected. So this is the result screenshot of performing this command file. You can find 2 different regions separated by different colors, a gray one and red one. Why they are different? Because they are belonging to different regions. But unfortunately, it does not specify the material parameter yet. So it, although substrate is maybe semiconductor, and substrate is semiconductor, and deep substrate is also the same material, semiconductor. However, they are just shown as different colors. So we are working on improving this situation, but for a while, just to accept this situation. And when you have a look at this inspector, multi-block inspector, then you can find that there exists deep substrate and substrate, and their names are specified in your command file. But maybe you can ask me this question. Well, although I just named it as deep substrate and substrate, but when I have a look at this inspector, there is a strange index 002 underscore 003 underscore. So I don't like it actually. I wanted to remove it. I tried, but due to the implementation purpose, unfortunately, I had to introduce these numbers. So it means that this is number 2 and this is number 3. Although this is the very first one, but it is named as numbered as 2. So what does it mean? There is hidden reasons in this program. So there is zeroth one and the first one. These two are special and not visible to you. So these two reasons are introduced to some garbage collection, or well, anyway, for that purpose, these two are reserved. So whenever you created very first one, then that is named as number 2. So for a while, just forget about their numbers, and you can just enjoy its name. So then maybe you can ask me this question. Then when I use Ångström-Craft, should I consider this naming? So it's not. Inside the Ångström-Craft, you don't have to worry about this naming. It is just added at the end of our calculation, and when the CGNS is saved, then we just name it with these numbers. So in your command file, just completely ignore these numbers. Okay? Do you have any question about? So I think that the best way would be just to log in the exercise workstation and type this this one. Actually, you can find it. So I will explain later. And another exercise you can do is, now your example, the very first one was so simple. So I wanted to recommend you change some parameters. So please do so. For example, change system size and change the thickness, initial thickness of the very first region. Instead of number 1, now say that 100. It means that you start from 100 nanometer thick substrate, and its name is no longer deep substrate. It is called as silicon underscore bulk. Whatever you call it, it will be respected. And another one is change output file name and change the spec for or deposition parameters for second region. Change its name, and thickness is now becomes 15 nanometers. So what you can expect is, this is the result of your exercise. then now you have 100 nanometer thick layer. On top of it, now you have 15 nanometer thick structure. That will be your result. Seems to be quite simple. So therefore, please do your own exercise. I already asked our TA to install the latest version. Well, I'm not quite sure he can do it properly because it's not his fault but my fault. So if he failed to compile it properly, then I have to fix it. So if that happens, do not blame him, blame me, and just report what happens. So then I will fix the problem. Okay. Then next one is silicon germanium multi-layer structure. Oh, up to now we just considered just silicon, but nowadays, although it is not related with the FinFET, but already when we consider nanosheet MOSFET, then we need multi-layer structure made of silicon and silicon germanium. So why it is used? Because silicon is still in many cases, except for TSMC. TSMC is known to use silicon germanium material as their channel material, starting from their 5 nanometer technology. They are known to do that. Also, they are known to sometimes they do and sometimes they don't do that. Well, they are just switching silicon germanium and silicon channel materials. But point is, whether you use silicon or silicon germanium, and anyway, you can make the multi-layer structure. And point is, silicon and pure silicon and silicon germanium have different etch rate to well-known etchant. So we can selectively etch silicon germanium, and just silicon can be remained in certain case. That is the trick. We can make nanosheet out of our planar structure. So I will explain later. But anyway, in order to make a nanosheet, we need this kind of a multi-layer structure. Then how can we prepare this structure in our Ångström craft? That is shown here. Of course, in reality, in order to make this structure in real fab, then we need a special facilities to grow silicon, and on top of it, we must grow silicon germanium. And silicon germanium have a different lattice constants, because silicons, they have a different lattice constants. That's the reason why when we just make it without special care, then between them stress occurs. Sometimes we can make advantages out of it, or sometimes we can take some disadvantages out of it. So careful evaluation is required. But in this case, we are just playing with such a structure, just like Lego, so we can do it quite easily. In your body of a craft statement, just to introduce multiple depositions sequentially. Orders are important. If you just swap the order, then something will change it. So, for example, if you just align silicon germanium first, all silicon germaniums are cold. After that, all silicons are cold later. Then the shape will be completely different. So it is processed sequentially. So please understand, it is important to have a correct appearance order. So let me just consider what will happen. Basically, we have a 100 nanometer thick silicon bulk as the initial statement and or initial reason, and it says that now we will introduce a reason called as a silicon germanium and whose thickness is just 15 nanometer. So we will have 15 and it will have a thickness of a silicon. It will have the name, reason name, silicon germanium. After that, the next one is a silicon and its thickness is just 5. And once again, silicon germanium, it is 8 nanometer thick. This is repeatedly done. What we have to be careful about these numbers is intentionally I made this number 5. So you can easily find that the thickness of our silicon layer is always fixed to number 5. Why it is set to be 5? Because this 5 nanometer is the nominal thickness of our nanosheet in the state of the art devices. So you can easily understand this one will be used as a channel material, and the thickness of 8 here means that now later when you make a certain transistor, we will have 5 nanometer thick silicon channel and 5 nanometer thick also silicon channel, just separated by 8 nanometer. This 8 nanometer difference or distance was maintained by originally by silicon germanium material. After that, this silicon germanium material will be etched away. Well, then they are still 8 nanometer away. Later, we will fill this empty part with very important elements like gate dielectric and metal. So that's the reason why we have a certain number. 8 nanometer. Is it good or not? Or is it thick or not? 8 nanometer is quite tight one because starting from this silicon and silicon, let's say that we have just 8 nanometer, and this 8 nanometer distance is shared by these 2 silicon layers. It means that for each silicon we have only 4 nanometer spacing for each channel. Within this 4 nanometer thickness, we have to implement high K material, also introduce gate metal to control our gate voltage. So it is quite difficult to have short distance like 8 nanometer. But we wanted to always to have a small number, because if we say it should be much larger, then the entire height of this structure will become too tall. So we don't want it. We wanted to make it as short as possible. Then you can ask me this question: why we need to have a short structure instead of a tall structure? Because if we make it too tall, eventually it becomes a certain tall and narrow fin. So although it looks like this, but during its fabrication it just becomes a fin, and it just become a fin, the neighboring ones. And it is well known that if we make such tall and narrow structures quite close together, then sometimes they are merged, or sometimes they are linked, and sometimes they are So that's the reason why we have to have a sufficient spacing between them, and we have to have also quite we have to maintain its what can I say, its height. If it becomes too tall and narrow, then it's like something like a paper, very thin paper. It is easy to be bended. You can easily bend it, but if we have a very short one, like this one, then it does not bend. It is not flexible. So that's the reason why we wanted to keep its height as short as possible. But anyway, in this representation, please remember that our coloring is not related to the real material index. This is just because this one is the very first one we have, and this one becomes the second one, and this one becomes the third one. So simply, when we swap the appearance order, then in this stage we will have different colors. But for a while, just live with this limitation, and I will try to improve this situation. Point is, in this current visualization, green regions are corresponding to silicon, and these are the candidate for channel material, and they are separated, and they are grouped actually. So you can find that two of them are quite close, and two of them are quite close, and two of them are quite close. So in this example, not realistic one, not realized in real technology demonstration or real device demonstration, I wanted to make one single device and another single device and another single device having two stacks in it. Okay, so anyway, the thing you have to do right now is just to log in your exercise workstation and just copy and paste this depot statement multiple times, and just to change the numbers, then you will have this one. And another thing you can have is, well, right now here I just named it with the same name, silicon germanium silicon, and here we have a silicon germanium, the same name. Therefore this one, I think that this one is recognized in the same region with this one. But if you say silicon germanium 1, silicon germanium 2, silicon germanium 3, if you assign different names to different regions, and then they will be recognized as a separate different individual regions. Okay, so it is easy to understand. Okay, then let's move on. So now exercise. Please note that it's not an official homework because I have no time to check your homework submission, unfortunately, due to my personal matter. So you can find the very initial one in our GitHub repository. I already uploaded it. Maybe you have seen it, and it is quite short. Please download it, and or you can just type in our exercise server, and you can just get the very first one. And starting from this simplest file, please try to generate all three structures you have seen, or you can play with different parameters. So you can do it quite easily. Then I think that this is the last slide of today's lecture. Up to now, we have discussed about two main topics. One was an overview about the companies which can fabricate FinFETs. Even though FinFET is not the state-of-the-art devices, already there are only 4 remaining companies who can fabricated. And if we go to nanosheet era, the number is even shrinking. So that was one thing. So another one was just to explain how can we use our in-house tool called or named as Armstrong Craft, and it has very simple grammar statement. You know only craft and depot. However, anyway, you have a statement and spec and body. So please do your own exercise. So starting from next lecture, lecture 7, we will start on inverter example, FinFET inverter example, and for that purpose, I will extensively rely on this well-known ASAP PDK. What is ASAP? Means that this is something related with Arizona State University, something like that. I guess that this AS is corresponding to Arizona State University, and AP is advanced PDK, something like that. And number 7 is corresponding to 7 nanometer technology. So please note that already in 14 nanometer or 10 nanometer were FinFET technology. So even in this ASAP7 PDK, they are assuming FinFET technologies. And if you ask me, is it realistic or not, then I have to say that no, it has not been actually manufactured in real case, but it can be regarded as a good starting point for our FinFET investigation. So in this ASAP7 specification, we have fin pitch of 27 nanometer. What does it mean, this fin pitch? Now I can explain it more clearly. Please have a look at, let me just magnify it. So now we have a very good example of a layout. Now I can explain what is the fin pitch. Here you can see this shaded line, and also you have this shaded line. These shaded lines are corresponding, these shaded parts, this is corresponding to a fin seen from its top view, and there is another fin and also another fin. They are separated with a fixed difference. So you know the distance is just fixed and distance is just fixed, but this distance does not show fin pitch. No, this is difference or distance between two neighboring fins, that is not corresponding to fin pitch. When we say fin pitch, then this is spatial period for this pattern, fin pattern. So it should be the sum of distance between them and also thickness of our fin. That is required. And in our assumed structure or assumed technology, ASAP7 technology, this distance was set as 27 nanometer. So this is corresponding to fin pitch. And let's go to another one, like CPP. Then you can see that CPP here. How can we determine this CPP? Here you can see certain, what is the color for this one? Yellow or orange? But anyway, you can find a certain box shown here. Can you follow my drawing here? And also we have the same color shown here. This is corresponding to gates. So the the pitch between two neighboring gate pattern, that is called as also a CPP. Then it means that CPP is not corresponding to just distance between two gates, but it should include also length of a gate. Starting from certain point, try to find out the same position with the same phase. Then this will be the CPP along, in our case, X direction. And in this case, I'm not quite sure the number, so let me just check the number. In this case, CPP is set as 54. So in this case, this is corresponding to 54. And yes, every pattern is just along this X direction. Every pattern is repeated with 54 period, 54 nanometer period. Then let's make a comparison with the realistic one, real fabricated one. For Intel 14 nanometer technology, it is 2 generations behind. So because ASAP is targeting 7 nanometer technology, so 14, 10, 7, that was the trend. So when we have Intel 14 nanometer technology, fin pitch was 42 nanometer and CPP was 70 nanometer. Already we have seen these numbers in our previous lecture 5. So compared with these actual number 42, 70, so our assumed number 27, 54 are much smaller. But please note that if we just follow traditional scaling rule, what happens? For each generation, X directional length scale, Y directional length scale is multiplied by 0.7. So if we just go 2 generation, then along each direction, we have to have just half of its length scale, the original one. So if we just believe that kind of behavior without any doubt, then I would say that so for 7 nanometer technology, Intel should have 21 nanometer for our fin pitch and 35 nanometer for our CPP. But what happens in this ASAP 7 PDK? Even for this virtual PDK means that in certain academic institution, without attempting to actually fabricate it, so they just suggest what will happen for next generation of our technology. In this case, even our virtual PDK, they say that 27 and 54, which is much more relaxed than the traditional scaling rule. So already you can see that in FinFET era, the area scaling or length scaling is much more degraded, and we cannot expect a rapid reduction of area as before, at least in this transistor level. And please have a look at this more realistic number. So what happens to TSMC 7 nanometer case? Fin pitch was even longer, 30 nanometer, and CPP was, they have 2 numbers, 57 and 64. This number is for high density, and this number for high performance. They allow their customers, if you want to have higher performance, then please take disadvantages in area. Or if you want to have more transistors, then please understand your performance would be a little bit degraded. They just suggest these two options. So anyway, the the reality is even worse than this ASAP7 PDK, but that was the situation. And Intel tried to, how can I say, keep the Moore's law, because Gordon Moore was their CEO, and they were so much stick to Moore's law, and their ambition was to keep this area scaling as much as possible. So they didn't announce their 7 nanometer technology, because from their point of view, TSMC's 7 nanometer is not actual actual 7 nanometer, because we have clear roadmap for next generation technology, but this one certainly doesn't meet that requirement. So however, in these days, who cares about the actual area scaling in transistor level? So we have to just break tradition set by ourselves. Who generated that kind of scaling rule and roadmap? They made it, and they tried to meet the requirement, and they already always succeeded to meet that requirement. Continuous success in previous decades was the main cause of their failure, because although transistor level scaling becomes too difficult, but they just try to do it because that was their pride and their success story, something like that. So anyway, so now they are changing. So I'm not saying that current Intel is doing so, but they made such mistakes. So please note that there is no real ASAP7 technology, but it can be a good representative example for 7 nanometer technology. You can see that a little bit more aggressive, and in this case we will use the use of EUV. So 7 nanometer was the transition period from normal previous DUV lithography to the EUV lithography. So some companies only adopted the EUV lithography, and someone denied to use it and keep the use of DUV. So for example, if we have a look at SMIC, they are still using DUV without EUV to fabricate their 7 nanometer technology. So, but in our consideration, we will just assume that lithography is not that difficult, because we will assume the use of EUV. Okay, so you will see what does mean in later lectures. And therefore, if we say Lx and Ly equal to 162 and Ly equal to 288, as assumed in our original startup kit example, it is corresponding to 162. The size of our x directional length scale is just 3 times of 54. What does it mean? We are now setting 3 times of CPP. Why we use 3 times of CPP? And actually this is the structure I wanted to make together with you in this classroom. So you can see that this distance is 54 and 54 and 54. Within these 3 CPP, we can implement our inverter example. So that will be 3 CPP long along x direction. Then how about this ly? This is corresponding to 288. Then it is not that much, not a multiple of 27. It is corresponding to 10 times of 27 fin pitch, and we have additional 18. Why we have additional 18? And this 18 is obtained from this 9 nanometer and this 9 nanometer. Between them here we have 10 times of fin pitch. So within this 10 times of fin pitch, we will implement our inverters. So why we need 10 fin pitches to implement this inverter, although we need just 2 transistors. If we have 2 transistors, then we can make an inverter. But why we need 10 fin pitch? As you can see here, now this is corresponding to this upper box is corresponding to our P MOSFET, and this lower box is corresponding to N MOSFET, and each N MOSFET, P MOSFET has 3 fins and 3 fins in it. So that's the reason why our entire length scale along y direction is almost 10 times of this fin pitch. Natural question is why we have to have 3 fins for this N MOSFET and P MOSFET. Why don't you just use 1 fin? If we use just 1 fin for each transistor, then we can save 2 fin pitches for this PMOS part, and also 2 fin pitches for PMOS part. Then instead of this number 2, with a simple argument, we can reduce it just to number 6. That is corresponding to 40% area reduction. Wow! But unfortunately, of course, you can understand if we reduce the number of fins by factor of 3, driving force, driving current will be also reduced by factor of 3. We cannot get sufficient amount of driving current. That is one thing. However, we have even more serious problem. At that time, 7 nanometer technology or 14 nanometer technology, people were not able to control our fins quite tightly. So if we just use a single fin and single fin, then we cannot guarantee that the performance of or characteristics of this single fin is identical to that of the near neighbors. They are fluctuating too widely because they didn't, engineers could not control the fabricated structure as tight as we can do right now. So they were worried about a variation. Oh, I allowed 1 single fin and I made billion single fin transistors, and their thickness are showing much variation, and our designers are complaining about just fluctuating electrical characteristics. So they were afraid of that, so they introduced just 3 fins or 2 fins. If you remember our previous lecture 5, you have seen the 2 fin device shown by Intel. So from the very beginning, so the number of fin was 2 or 3. So 3 was the nominal one and 2 was regarded a little bit small one. Anyway, multiple fins were required to have well-controlled behavior. What happens at the end of our FinFET era? When we go to the end of a FinFET era, engineers becomes quite much skillful about fabricating FinFET, so they were able to allow single fin device. So TSMC allowed single fin options for their last FinFET technology. So if you allow from two fin device to one fin device, if we consider just a single device, this is corresponding to 50% area reduction. Of course, we have to consider other parts, but that is a real drastic reduction of area. However, always variability makes some resistance against reducing fin numbers. Okay, so I think that's it for today's lecture, and let's go to the real fabrication on this Wednesday. Thank you and bye.